So in this video, we're just going to go over a couple more examples of integration by parts, including some more complex double integration by parts and some trigonometric integration by parts, starting with a very simple problem, which I will write out right here. Okay, as you can see, I have the integration by parts rule up here for reference. And we're going to start by picking our u. If you look at this problem, right, you only see one function right here, which is ln x, but there's sort of a hidden function, which is times 1, that you can bring into an equation like this to find this integral. And so I'm going to make my u equal to ln x, making my derivative of u equal to 1 over x. And I'll explain why I didn't choose 1 in a second here. Therefore, I'm going to be making my derivative of v equal to 1 and the integral of v equal to x. The reason why I didn't make my u be 1, right, you might think that is the most simple function that I could have chosen for u, is because when we get to this integral right here in our rule, we're going to see that we need the derivative of u times v. We're going to have to find that integral. And if we chose 1 instead of ln x for our u, we would end up having x times, right, the integral of ln x, assuming we chose ln x to be our derivative of v. And obviously we cannot put the derivative of v to be our ln x, because when we try and find our v, right, we're just going to run into this exact same problem. So the only u that we can use right here is ln x. And now I'm just going to write out the problem. Right, so this is the setup of our integration by parts, and now we're just going to go through solving it, which we say that this is just equal to the ln of x times x, right, that's our first part, minus the integral of x over x. X over x is just 1, so we're just looking for minus the integral of 1, and the integral of 1 is just x, when differentiating, of course, with respect to x. So we are integrating with respect to x, so we're just going to get minus x, right? Simple as that. The next integral we're going to solve is x times sine 2x. And just a standard procedure, right, I'm going to make my u be equal to x because it's the most simple function, and I'm going to make my derivative of u, or u prime, equal to 1, right, because that's the derivative of x. And I'm therefore going to make my v prime equal to sine 2x. Then I'm going to make my v prime equal to sine of 2x. And that means the integral of sine of 2x, right? Let's just integrate sine of 2x here real quick, and then we'll erase it, right? We're going to do a quick u substitution equal to 2x. So our du is equal to 2 dx. And because we don't have a 2 here, we have to multiply by 2 over 2, which gives us 1/2 of sine of u, right? That dx and that top 2 cancel out to give us a du. And then we plug in our sine, or our u for 2x here, and so that's just going to be the negative cosine of u, which we said was 2x, over 2, right? The integral of sine is negative cosine. We get the 2 on the bottom from this 1/2, and our u is subs back in for the 2x. So we can write this as negative cosine 2x over 2. Now we move on to setting up our integral very formally from what we have just created. So we're going to say the integral of uv prime is the u, right, times the v, right, so we got negative cosine of 2x divided by 2, like so, minus the integral of u prime, which is just 1, times u prime, which is just 1, times the integral of negative cosine 2x over 2. Right, now I can rewrite this entire thing, right? We're just going to make this one our final. So we're going to go, the integral is equal to negative x cosine 2x over 2. And I'm going to say plus, right? Because this negative, based on the constant multiplier rule, can be drawn outside. And a negative times a negative is just a positive. So plus the integral of cosine 2x divided by 2. Now I'm just going to solve for this integral right here. So I'm going to draw the 1/2 out, right? That's where that bottom 2, that's where it comes from. And I'm going to get cosine of 2x. Then use a u substitution of 2x and then du is just going to be equal to 2 dx, right? Because we're differentiating with respect to x here. And then I'm going to have to multiply again by a 2 over 2, right? So I have to multiply by 1 again. You get 2 over 2 times 1/2, right? Times cosine of 2x dx. And that dx, that 2, right? They give us a du. And then that 2x, that becomes a u. So we can rewrite this integral as 1/2 times 1/2, which is just 1/4. 1/4 the integral of cosine u du. Alright? And that is just equal to sine of u, which we said was 2x, right? Divided by 4, because that's where that 4 comes in. So the integral, this integral right here, right, is sine of 2x divided by 4. And if we clean this up, we get this entire thing as our final integral, right? You could simplify this further if you need to by multiplying this side's top and bottom by 2, so that you get, you know, the sine of 2x over 4, right? Minus multiplying this top and bottom by 2, minus 2 cosine 2x divided by 4, and then you can combine those together because they have a common denominator into sine 2x minus 2 cosine 2x, right, all divided by 4. So the next integral that we're going to do is x squared ln x cubed. And the u that I'm going to choose, that's the u that I'm going to choose. And I'm choosing that u because it's hard to find an integral for ln x cubed, right? X squared is definitely simpler than ln x cubed, but it is more complicated to find an integral, assuming we make our ln x cubed, assuming we make it a v prime, right? It's harder to find that integral, and because I don't want to find that integral, I'm not going to use that for my u, or for my v. I'm going to use that for my u instead. And so the derivative, right, is just going to be the outside function, which is ln x, so we get ln x cubed, because the outside function is ln of your function, times the derivative of the inside function, right, which is ln x squared. The inside function is x cubed, so the times the outside. This is just the chain rule, and this can be rewritten as 3 over x, right, because that 3x squared goes into the numerator, and that x squared cancels out 2 of the 3 x's in the denominator, and then we get left with, or 3 over x. And then for my v, right, I'm going to write my v prime as equal to x squared. Therefore, the integral of v is just going to be x cubed over 3, right? That's my integral. Now we're going to attempt to solve this. So we're going to plug in our u, right? We get ln x cubed. Then we're going to plug in our v, x cubed over 3. And then we're going to subtract the integral of u prime. U prime is just 3 over x, right? Times v, and v is x cubed over 3. And now we can simplify the expression here. This integral can be rewritten where these 3's cancel out, one of this x cancels out, and then it just becomes the integral of x squared. And the integral of x squared is very simply x cubed over 3. So our final integral is just going to be the first part, right, which is ln x cubed times x cubed over 3 minus x cubed over 3. That is our final integral for the whole problem. This is solved. So the next problem that I'm going to solve is going to require a double integration by parts, right? We're going to have to use integration by parts 2 times. And so let's just do it the first time, right? And I'm going to go kind of through this quickly because we've already done 3 examples, and I think you should get the point by now. But let's do our u. I'm going to choose my u to be x squared because it's very simple, which means the derivative of u, or u prime, is just going to be 2x, right? And then I'm going to make my v prime equal to e to the negative x, and my v is going to be equal to negative e to the negative x, right? You can verify this for yourself. If you take the integral of e to the negative x, you're going to get negative e to the negative x. It requires some substitution. And then I'm just going to set up my integration by parts right here on the right hand side. So as you can see, my setup is u, which is just x squared, times v, which is negative e to the negative x, right? So I put my negative just on the outside for convenience. And I did minus, right? But we're subtracting the integral of 2x, which is the derivative of u, times v. And v is negative e to the negative x. So I just dragged the negative outside of this integral for convenience, placing it on the outside right here to get a plus. So this is just plus the integral of 2x e to the negative 2x. And this right here is an integral where we need to use integration by parts again. So I'm going to write that down in the bottom left. Now I'm going to do a different color to show that this is the second integration by parts. I'm going to go u is equal to 2x. U is equal to 2x so that my u prime is just equal to 2. And then I'm going to make my v prime equal e to the negative x, which means my v is going to equal negative e to the negative x, right? I'm doing it similar to last time just because of convenience. And now when I set up my new integral, I'm going to get when I set up my integral, I'm going to get u, which is 2x, times v, which is negative e to the negative x, minus the integral of 2 times negative e to the negative x, right? But what I did is I just took this negative with the constant multiplier rule and I brought it outside, and negative times negative is a positive. Now this integral does not require the integration by parts rule. You can solve this very simply, right? We can just say the integral of 2 times e to the negative x, right? And we know that that equals negative 2 times e to the negative x. And so we have our very final integral is going to be negative x squared e to the negative x, right? And that just comes from right here. And then we're going to add to it the integral of 2x e to the negative x. And we determine that the integral of 2x e to the negative x is equal to negative 2x e to the negative x plus the integral of 2e to the negative x. And we determined that the integral of 2e to the negative x is just going to be negative 2e to the negative x. And this is our final integral. Of course, put the c. I'm usually very lazy. I don't put the c. And you could simplify this further, right? We notice that there are, each one of these is negative, and each one of them has an e to the negative x. So you could go e to the negative e to the negative x times, right, x squared plus 2x plus 2. This could be your simplified version, because when you multiply negative e to the negative x by each one of these, you're going to get this right here. And that's the final integral for this particular problem. Next, I'm going to do a very, very tricky integral. And when you're working with trigonometric functions, you may have to, especially with e's, you may have to think about this, right? So we're going to go e to the x cosine of x, right? This is our integral. Now, I'm going to make my u be equal to e to the x, which means the derivative of u is just e to the x. And I'm going to make my v prime be cosine x, which means my v is going to be equal to sine x. This is actually kind of arbitrary because both of these are pretty complex functions. I guess this is a simpler derivation right here. E to the x just goes e to the x, so I chose that. But otherwise, it's relatively arbitrary. You could choose something else, and if you find it's too hard to follow, you can get rid of it and change it up. And so we're just going to integrate this, right? We're going to use our rule right here. Right, now we're stuck with this e to the x sine x. This is another integral that we're going to have to do integration by parts. So I'm going to write this down as a new one right here. So e to the x sine x, okay? And of course these are all with respect to x, my bad. And I'm going to make my u be e to the x, which makes my u prime be e to the x. And I'm going to make my v prime be sine of x, right? So that my v is going to be negative cosine of x, okay? And now I'm going to set this up. Now, if you haven't noticed by now, this is just going to repeat itself, right? It's going to go back, it's going to complete another loop. And so what we can do is create a system of equations. And I'm just going to write these down so you can notice this pattern here. Right? Our two equations are so this has now become virtually a series of equations, right? This e to the x cosine x is just equal to this right here, which we have written as the first equation, and this e to the sine x is just equal to this right here, which we have written as the second equation. And as always in a series of equations, and I'm going to just solve them down here and then we can move back up afterwards. As always in a series of equations, right, we're really trying to find this. This is what we're really trying to find. You can think of this kind of like an A, and think of this as almost like a B, and you can think of this as a B and this as a right here. And what I want to do is rearrange one of these equations so I can substitute it into another. And since our original integral is asking us to find e to the x cosine of x, I'm going to try and sub in e to the x sine of x in terms of e to the x cosine of x, right? So what we're going to get is this. I sub this in right here, and then I'm going to get e to the x sine of x plus e to the x cosine x minus e to the x cosine x, right? And now I can add this cosine x on both sides so that I get 2 e to the x cosine x, right, equals e to the x times sine of x plus cosine of x, right? All I did here was I added this on each side to give me 2 e to the x cosine x, and then I dragged this e to the x and I dragged this e to the x outside of the sine x plus cosine x, right? If you just multiply this by e to the x sine of x plus e to the x cosine of x, it's the same thing. And then I divide by 2 on each side. So our final integral, right, because the original integral that we were trying to solve was our final integral is just going to be equal to e to the x sine of x plus cosine of x, right, all over 2. And this is not just trigonometric. You may run into problems, especially when you have e to the x and you have to use it for convenience as a u, right, instead of a v. You may run into problems where they have this loop. And so what you need to try and do is, after 1 or 2 loops of integration by parts, you need to try and find a system of equations where you can substitute in one of the equations to get something like this. And this is your final answer for this. And this is the challenge problem. And that's all.